Okay, so this talk for today is reserved for the platinum partners of this year's conference, Rivian, who have significantly contributed to everything we envisioned. And now we have Aleksandar Cvejic, team lead for data platform and ML infrastructure, autonomy, and AI at Rivian. Aleksandar will be presenting Rivian Autonomy and AI, building a scalable platform for data and ML workloads. In this session, he will share insights into how Rivian developed a scalable platform to manage complex data pipelines and ML workloads for its advanced driver assistance systems. Aleksandar will provide an overview of the architecture and infrastructure for orchestrating ML workloads, along with custom-built tools to support these processes. Please welcome Aleksandar to the stage.
Hi, everyone. So there goes my intro. So my name is Aleksandar. I'm a lead of data application ML infrastructure team. We are part of the Autonomy and AI organization at Rivian. And together with our colleagues from US, we are managing and maintaining cloud infrastructure and cloud data platform. So today I'm going to speak about some of the ADAS challenges. ADAS stands for Advanced Drivers Assistance System. So some challenges that we were facing, that we tackled, how ADAS looks at Rivian, the data platform that we built to help us manage that complexity. We call it Polaris apps, and dive a bit more into simulations and ML workloads. So let's go and see those trends and challenges. So data in autonomy is vast, complex, and scaling at immense levels. So to process that data, we have many processes that we need to orchestrate and always be faster in that process. So to give you a picture about data variety, you can see that we have here 11 cameras providing 55 megapixels of real-time imaging at state-of-the-art resolution and dynamic range. We have 5 radars enabling advanced multimodal sensing with a 300 meters of forward-facing detection range. We also have 360 degrees of sensing with overlapping sensors, providing redundancy, robustness, and performance. So that data variety translates into data volumes. So you can see here on this chart, in the previous 6 months, our records per day grew from 6 billion at April to 40 billions at May to 2 trillions in October. That translated into volume of data that we manage that grew from 14 terabytes in April to 50 terabytes in May to 1.6 petabytes in October. So doing any optimization at this scale translates into hundreds of thousands of dollars saved in both cloud costs and engineering working hours. But we couldn't just keep up with that data volume and variety. We had to also improve ourselves. So you can see here, we reduced our SLA from 150 hours in April to 38 hours in May and 4 hours in October. SLA that we are keeping a close track to is data availability. So it measures the time from the moment when event happened, it is recorded in our vehicle, to the moment when that data, that record is available in our platform to be used for. So data volumes, I mentioned this data. So let's see how that data life cycle looks in ADAS. So from the bird's eye view perspective, it's quite simple, not too complex. Data is created, is uploaded into our cloud, processed, then using data sets, model is trained, and then that model is deployed to our vehicles using OTA, over-the-air deployment. I said pretty simple from the bird's eye view perspective, but if we dig a bit deeper into that processing that I mentioned, you can see that there are more than few steps that we do in our data pipeline. Software ingestion, we do metadata tagging, curation, labeling, dataset management, of course, model training. We do simulations, and yeah, it's complex pipeline with the complex steps. All of those steps were tackled by building some tooling, applications, pipeline during previous years. So many teams solved same issues, for example, with a different approach, and it was hard to maintain and scale. So we decided to build a comprehensive, centralized platform to manage all this data pipeline. We call it Polaris Autonomy Data Platform. Think of it as a backbone for data operations at ADAS. It's a operating system for ADAS data. So we had a few guiding principles when we were building this platform: ease of use and reusability, data management, governance, and security always in a data field important, operations automation to enable users, engineers, and business folks to do data visualization and analytics, and support simulations and ML workloads. To help us do that, we build a suite of apps there. I will mention just a few. Data discovery, used for search for advanced filtering over our data. Metadata management framework. It's used to enrich our data with metadata tags, and essentially it empowers all other applications in our platform. Labeling, we do both in-house labeling. We use third-party provider labeling providers. We build tools and applications for that. We build pipelines to integrate with those third-party providers. We build auto labeling pipelines, visualization. We have a Polaris Viz application, which is a fork of open source application called Foxglove. We enriched it to support Rivian data format. We built an extension framework around it. We support both web and desktop version. SimDash for simulations, Cosmo and Rivex. I will dwell into those a little bit later. So, building Polaris data platform help us enable engineers to focus on innovation instead of infrastructure. So if we go back to that data loop that I was showing a bit before, let's reiterate over it, but using ML workflow. Again, data is created, recorded, uploaded, then it ends up in our cloud. It ends up in S3 buckets, and then event-driven architecture is triggered using SQS and Argo workflows. It starts processing that data, and we use AWS Batch for compute layer there, and it helps us orchestrate and not worry about underlying infrastructure and scheduling. After the data is ingested and processed, we can use those data sets for model training. For model training, our compute layer is EKS. That's AWS's Kubernetes managed service. On top of that, we use KubeRay operator for orchestrating trainings, MLflow for experiment tracking, for checkpoints during preemptions and similar stuff. Once the model is trained, we go to simulation and validation. We trigger simulation by using that git hash of the model. Again, AWS Batch kicks in, does simulation. The outcome of the simulation goes into S3 and then into Databricks for analysis and visualization. Once we are happy with the KPIs with our model, it goes back to our vehicle. So let's go into simulation and model training infrastructure. So simulation architecture, we build a SimDash app, which is an entry point for all engineers and users for managing simulations. We have two main workflows there. On demand, where an engineer can select a git hash and data set on which they just schedule simulation. The other one is scheduled. Additionally to Git hash and data set, engineer can select a schedule, Chrome-based schedule. In the background, event bridge schedule will be created and will trigger simulation periodically. In either way, it again triggers AWS batch, outcomes go, results go to Amazon S3, then into Databricks to be used and to be used for analysis. For visualization, I mentioned Polaris Viz already. We use Streamlit to build dashboards for both business folks and engineers. We use AWS Batch, as I said, to offload many of the managing work there, like orchestration, worrying about availability of resources and similar, and that helps us scale 200x compared to our previous infrastructure that we built, that we were using. But it also come with some downsides, bottlenecks. So first bottleneck that we tackled was TPS, transactions per second. It's a hard quota limit imposed by AWS. It represents how many jobs we can schedule per unit of time, let's say hour. So we tackle that by bundling multiple jobs into one job, into one container. So if we bundle 3 jobs into one container, we managed to improve our effective TPS by 3x. Other bottleneck, startup time. It was more optimization, cost optimization, and performance optimization. We use quite large Docker images. So in the initial spin up of our EC2s, it would take like 6, 7, 8 minutes to even start the simulation. So we tackled that, of course, by slimming down our images as much as possible, but also to caching Docker images into AMI. The third one is large simulations. When the large simulation, let's say, of more than 1 million jobs would kick in, it would completely hog the queue. And no other simulation, no matter how small, could go there and be executed. We tackle that by implementing fair share policies, where we leverage things like share identifier, weight factor, share decay, compute capacity reservation, and similar stuff. If you didn't figure out already, all of our infrastructure is on AWS. So if we go, let's go to ML infrastructure. Bottom layer, let's call it like that, we use different AWS offerings of the services, Amazon EC2 for compute, CloudWatch, Managed Grafana, Managed Prometheus for monitoring observability, Amazon S3 for storing our data. On top of that, we use EKS for orchestrating that computation. First layer, let's call it plugins into EKS. We have a suite of plugins that we deployed there, EFA, FluentD, EBS, EFS, S3 for data layer, and GPU operator. EFA is an interesting one. It is used for GPU to GPU communication, where and it reduces latency during the communication between those GPUs and improve our time. Another one is an interesting one is a GPU operator. It essentially exposes underlying resources, GPUs, as Kubernetes resources. So the user engineer can schedule a job and use any amount of GPU available there. Next layer is a job management layer. We use Kueue. It's an open source plugin from Google. It's used for job orchestration. It has a gang scheduling. It enables us to do preemption and that kind of stuff. We use Ray job operator for syncing those jobs and orchestrating the training, and we use PyTorch. On the top layer, we have actual Ray jobs that are running and that are doing model training for us. And we use MLflow, like I already mentioned, for experiment tracking, for model artifacts, checkpoints, and similar. engineers interact with this infrastructure using two apps that we built, Rivex CLI and Polaris Cosmo. Rivex CLI is a command line tool with a few commands like train, attach, list available resources, yeah, and similar. Rivex, we have something that we call backends there. We built backends in order to help engineers do model training more in a smoother way. So backend can be local engineer laptop, it can be Ray cluster or a Ray job. How engineer interacts with a Ray job is by creating Rivex config in which it can specify like dependencies on which cluster name it wants to run, cluster region, image, resources that wants to use, like run on P548X large, this much GPUs, priority, and similar. Rivex communicate with the Kueue, and Kueue, based on the resource requirements, decides on which flavor of resources we schedule these jobs. We have also a thing we call spines on AWS, like same resources can be split into different regions or availability zone. So for improving our latency and model training, we can define one spine that is physically where the resources are physically close by, and we want to run training only of those. So as I mentioned, we use Ray jobs for training. Ray job is a part of the KubeRay operator, and what it does, it spins up Ray cluster for that training only. The model is trained. Once the job is done, it destroys the Ray cluster. In that way, we optimized resource usage and also remove single point of failure that we had with long-standing Ray clusters. Before starting to use Ray job Ray clusters, if we had any issue with the cluster, it would affect all the jobs running on them. So this helped with that, but it made harder for the engineers to track the experiments, to see logs, to debug, etc. So we had to build observability framework around that to help them visualize what's going on with their training. We use Grafana for that, and it's pretty much straightforward. You can select your job, you can see average GPU utilization, running pods, running workloads in Kueue, and similar. This is AWS managed Grafana. So all the user has to have access to AWS, has to know their way around it, has to be well-versed in using Grafana, and I think each user for managed Grafana needs to be paid to AWS. So we went to our principles and we brought this back to our platform Polaris, and we built Cosmo. Cosmo is used for tracking our trainings, and on the landing page you can see something like cluster metrics, like running workloads, pending workloads, number of GPU nodes, and similar. Then you can go into job tabs, jobs tab, where you can see running jobs, completed jobs. You can filter out, you can search for your own job, and maybe go into that job and see what's going on there. Again, see similar thing as on that Grafana dashboard, number of worker pods, GPU utilization, object store memory, and similar. And yeah, these are metrics, and you can see also logs there and see what's going on there. This is all I wanted to show you about our Polaris platform. So what's next? Always improving stability and optimization, both in cost and performance, and improving capabilities by building new apps or adding features to the existing apps, like maybe moving Rivex to Cosmo and making Cosmo single entry point for all ML related work. If you remember one thing from today's talk, I would prefer to be this chart that I showed at the beginning. So in the last 6 months, our RPDs grew by 300x. total volume of data that we manage grew 150x. We reduced SLA by 40x. So ADAS field is ever-changing. The requirements are growing. So yeah, the only constant is change. Rivian is adding new vehicles to our fleet. We are expanding on the new markets, and the data volume and complexity will continue to grow exponentially. So we don't know what will be required from us in a year or 2 or 3 from now. But that's why we have a Polaris, which is a powerful, scalable, and user-friendly platform that keeps us ahead of curve. So yeah, thank you for your time. I will take any questions if you have.
Hey, thanks for the talk. I was just wondering what data format you use to store the data in on S3.
We use Parquet mostly. We, again, bunch of different formats, but we are focusing to use Parquet, you know.
So it's just raw Parquet, or do you use some sort of like Delta Lake or Iceberg? Or...
So I don't have an answer to that question. I'm more focused on infrastructure here and yeah, in the architecture. So let's talk later and I can find out that information for you.
Okay, thanks.
No worries.
How actually Rivian learn what framework? Sorry for question, but how Rivian learn which model they use?
We are training our own models, but yeah, again, that's more into the model itself, and it's a question for our ML engineers. I can get that answer for you. Sorry to answer it like that again, but yeah.
Thanks for the presentation. Really interesting and detailed. Thanks a lot. So I would have a question more or less about like infrastructure. You did it on the cloud, but still you did a lot of open source tools, Argo, Kubernetes, operators, and so on. So more or less, yeah, we did something similar in the few years ago, but I'm just interested like comparing to out-of-the-box technology, for example, at AWS maybe gives about training the models, pipelines on their own. So what is the, like, is it cost reduction at the end that you did a lot of custom things, or there were some limitations for these big scalable platforms? Yeah.
So it's mostly limitations. Cost is like number one always in every discussion that we have, but we are on AWS and there are partners and we closely work with them, but everything else we try not to use like third-party solutions. We use open source, or there isn't open source that can satisfy our needs. We build our own.
Okay. Thanks a lot.
Thank you, folks. Bye.